lesson today is us working with square root expressions, and we're going to work on what's called simplifying them. Um, it is a fairly straightforward process, and some of you have done this. I think you might have done this a little bit in geometry. There's lots of different ways of how we can go about doing this. I do it in a specific way that to me is the most efficient way to do this. But the whole reason why we do it is it helps us keep our answers exact, because when we're dealing with square roots, a lot of times when you take square roots of a number, it becomes irrational, meaning that decimal is going to go on for forever. So the whole point is to simplify these expressions to get it in its simplest terms. So in algebra, we'll often need to reduce radical expressions. When you move on to pre-calc next year, this is something you do every single time that a radical expression shows up. This process requires you to factor out any perfect terms, and I'm saying perfect because we're just working with square roots. You could work with cube roots or fourth roots or fifth roots, and the perfect terms or the perfect numbers are a little bit different then. We're just going to focus on square root terms by factoring out perfect squares. In general, it is best if we can factor out the largest perfect square from a square root term. That's going to always be our objective. So the first thing I want us to start with is just reminding what the perfect squares are. And a lot of times if you struggle with this and you're like, hey, Mr. Younger, I need help reducing this square root, I will ask you to do this right away, okay? Because a lot of times if we can see the perfect squares, we know what we need to be dividing by. So remember that the perfect squares are us taking each integer, so each whole number, and just squaring them. Okay, so 2 squared, that's 4. 3 squared, that's 9. 4 squared, 16. And we're going to go all the way up to, they really don't stop. They are infinite. But let's go to about 12. We'll go to like 14 squared. And these aren't numbers you need to memorize because you can make this list really quickly just by doing exactly what I'm doing right now. Okay, taking each whole number and squaring them. So 9 squared, 81. 10 squared, 100. 11 squared is 121. Yeah, I'm going to run out of room. We'll go to 12 squared. 144. But know that that list continues. Okay, so the perfect squares are these numbers on the bottom here. So 4, 9, 16, 25, 36, 49, and so forth. And so the reason that we factor those out is because we can take the square roots of those. And by taking the square root, that allows us to reduce down each radical. So when I'm trying to reduce down a radical, I'm always looking for the largest perfect square. It doesn't have to be the largest perfect square, but you'll see that the process is much more simple if we can get that largest perfect square factored out. So what I do is I go, okay, I got 12 here. The only numbers that I want to check to see divide 12 are these perfect squares. I don't want to list just any numbers that divide 12. I only want to factor out from 12 a number that is a perfect square. And the only perfect square that is going to divide 12 is 4. So when we do this, and be very specific with your notation here, we are factoring the square root of 12 to be the square root of 4 times the square root of 3. Keeping that square root term there, or that square root operation in the number, is so important because it helps us keep track of, okay, what is the radical term still, the root 3, and what numbers can I take the square root of? Well, the square root of 4 is 2. And once I take the square root of that, that symbol is gone. And so after I have factored out a perfect square and taken the square root, I circle that, saying that that is a dead end. There's nothing more that I can do to simplify that. We've taken out the perfect square and then taken the square root of that number. We then just want to make sure that root 3 doesn't have any other perfect squares that divide it. Obviously it doesn't, right? 4, 9, and 16, etc. won't divide 3, so that is also a dead end. And if we take out the largest perfect square, this is the most amount of work that we need to do. Okay, if you don't take out the largest perfect square, you have a little bit more work that you would need to do to simplify this. So the square root of 12, that is equal to 2 times the square root of 3. And this is an easy check. I can see, is the square root of 12 equal to 2 times the square root of 3. It should give me the exact same decimal, and it sure is. Okay, so let's do root 80, and then I'm going to show us just what happens if we end up dividing by not the largest perfect square, but just some other perfect square. 80 may not be the best example for that, but let's see. So I want to divide 80, and again, I'm looking for the largest perfect square. So I'm looking at my list, and I'm like, okay, what could be the largest perfect square that divides this? Well, maybe 49. But I know that 49, that's more than halfway to 80, right? So I already know that if I take 80 divided by 49, it's not going to work. And so the largest perfect square needs to be at least less than halfway to that number. Okay, so the first perfect square that might work is 36. So I just take 80, I divide it by 36, even if I know it's not going to work. Okay, doesn't give me a whole number, so I don't like that. So I'm like, okay, what about 25? Nope, doesn't work either. And then I just keep going down. Okay, so what about 16? Ooh, 16 and 5. And so 16 is the largest perfect square that divides 80. So we're going to factor the root 80 to be root 16 and root 5. Again, I'm keeping the square root terms there until I actually take the square root of the number. The square root of 16 is 4. Root 5, there aren't any other perfect squares that divide that. So root 80 is equal to 4 times the square root of 5. All right, so let's pretend that we didn't see the 16, that somehow we skipped it over and we just said, hey, I know for sure that 80 is divisible by 4. And so instead we factor this to be root 4, and then 80 divided by 4 would be 20. So I get root 4, root 20. Well, root 4 is 2. That gets me that dead end. But root 20, it's still possible. There's a perfect square that divides that. So it's almost as if we restart with root 20. And I say, okay, what is the largest perfect square that divides 20? Well, that's going to be 4 again. And so I factor root 20 one more time to be root 4 and root 5, where the square root of 4 is 2. So now I have a 2 as a dead end, another 2 as a dead end, and a root 5 as a dead end. Well, all of these terms, really what's happening, they're all being multiplied. So when we get to the very end and we have multiple dead ends here, we just need to multiply all of them together. 2 times 2 is 4. Root 5, we can't really multiply to combine it, so it's just root 4, or excuse me, 4 times root 5. Exact same thing we got previously. So do you need to factor out the largest perfect square? No. Okay, but you can see it is a little bit quicker for us to get there and a little less complicated. So that's why I'm going to always encourage you to try to get that largest perfect square. So when you're first dividing, start with bigger numbers and work your way down. All right, any questions here with where any of these numbers are coming from, any of the square root operations, or any work I've covered thus far? Okay, I'm going to do this one down here and then have us do these last two before we move on and talk about one other thing. So the difference with these two down here, 8 root 448, is we have a dead end already. This 8 is part of the term. So I just circle that, and I know that at the very end, I need to divide by that, or excuse me, multiply that 8 by any other number that is not underneath the square root symbol. So then I'm like, okay, 448. Well, our perfect square list, we only went to 144. I could make a bigger number that's not on there and try to find a bigger perfect square that might divide 448. But let's just stick with the ones we have up here. And more than likely, I'm going to have to do it this second way where I probably won't find the largest perfect square that divides it. So I'm literally just going to start with the largest perfect square I see in front of me, which is 144. And I'm going to divide it until I get a whole number. And I'm starting at the largest perfect square and working down. If you have a good number sense, you can skip some, like 100. I know 100 doesn't divide 448. So I'm going to skip that. So I'm like, okay, what about 81? Nope. So I'm like, okay, what about 64? Yes, 64 and 7. So root 448, I can factor to be root 64 and root 7, where the square root of 64 is 8, and the square root of 7, this actually worked out really nice where that was the largest perfect square, right? Taking out root 64 left us with root 7, which doesn't have any other perfect squares that divide that. So that part is done. So now, multiplying our dead ends, including the 8 from our start, 8 times 8 is 64, and then times root 7. Again, that seems weird, because I'm like, 64 times root 7, that seems like a big number. So I'm just going to check this one. And then square root of 448. Something went wrong. What did I do wrong? Huh? Forgot the 8? I got the 8. 8 times 8. Was 448 divisible by 64? Yeah. What the heck? Oh, I see. I see. I forgot the 8 right here when I did 8 times root 448. There we go. You were on it, Casper. Now they're the same. Yeah, I just forgot to multiply that 8 by the root 448. Good catch. Okay. I want you all to try -3 root 32 and then square root of 128. And then I have one more thing we're going to add to this, and then we'll get you some work time after that. Pause the video. Okay. Let's see how we did. I'll zoom in here so we can see a little bit better. Starting with the square root of 128. Root 128, the largest perfect square that divides it is 64, making that root 64 times root 2, and the square root of 64 is 8. So that is 8 root 2. It is not the only perfect square, so you could have also divided it by 16 by 4. If you do that, you're just going to have a couple more steps to ultimately get it completely simplified. Okay, but root 128 is equal to 8 times the square root of 2. And then the last one here at the bottom, -3 root 32. The largest perfect square that divides 32 is 16. So I factor root 32 to be root 16 and root 2, where its square root of 16 is 4. We do have that coefficient of -3, so -3 times 4 is -12, and then times root 2. Okay. Any questions here before we just add one small piece to all this? Okay. So now, we've mentioned this before, but what if we went to take the square root of -24, let alone not even just reduce it, but if I tried to take the square root of this, we run into a problem. Okay, the calculator will tell us that it is a non-real answer. And up to this point, if we took the square root of a negative, that's basically what we concluded. This is a non-real answer. It's not a solution. But now we're going to add something into this that allows us to work with negative square roots. And this is a really important piece as we progress into the lessons that show up tomorrow on Friday, but then even into our next unit that will start when we come back from the break. Okay, so can the following square root be taken? You know what, let's just add right into it. Let's start here. Okay, answer was no. We can't take the square root of it without it being real. Okay, but taking the square root of a negative number results in what's called an imaginary number. So square root of a negative is what's called an imaginary number. Okay, it is also referred to as a non-real number. So if you hear either one of those, it's referring to it being imaginary. And in order to get solutions, we need to factor out the negative. So mathematicians, they wanted to still get solutions to a quadratic and eventually higher degree polynomials. That's what our unit will be when we come back from break. And so they said, you know what, let's find a way to define this negative and still work with square roots. That way we still get solutions. They're just imaginary. And these imaginary solutions, they have more complex applications that we don't really get into in this class. In fact, you don't really get to them at all in high school math. That's like way more down the road. But there are applications to these imaginary solutions. So basically, the imaginary number represented by the variable I is equal to the square root of -1. So anytime that we are asked to take the square root of a negative, we need to factor out the -1, okay, or take away the square root of the -1. And then from there, everything else is the exact same. So really not much is going to change here. It's just that we're going to say that it's imaginary, and then the rest of the process from there is the exact same. So for example, square root of -200. I know that's not a real number. But if I factor out the -1 and call this the square root of -1 and the square root of 200, well, the square root of -1, that's I. That is a dead end. This solution is imaginary. And then I deal with the square root of 200 exactly like what I did on the front by factoring out the largest perfect square that divides 200, which is 100. So that's 102. Square root of 100 is 10. The square root of 2, there aren't any other perfect squares that divide that. So this is equal to, and there's multiple ways to write this. You could write this, the most natural way is to say 10 I root 2. And really what's happening between the 10, the I, and the root 2 is they're all being multiplied. So the order in which you write these three terms, it doesn't make a difference. You could say I 10 root 2. You could say 10 root 2 I. Hey, it really doesn't matter how we write the order of all three of these terms that are being multiplied. This is the most natural, the 10 I root 2, but I wouldn't count it wrong necessarily. Okay, let's do this root -96. I'll have you do these two on your own, and then that's it for this lesson. So you don't need to necessarily show the factoring out of the -1. You could just right away say, hey, root -96 is equal to I times the square root of 96. Okay, and just take the square root of the negative right from the start. Now I'm off to checking any perfect squares that divide 96. Let's see, about halfway would be 49, so it's 96, 49, that's not going to work. What about 36? I don't think so. 25, definitely not. So what about 16? Ooh, there we go, 16 and 6. So root 16, root 6. Root 16 is 4. Root 6, there aren't any other perfect squares. So this simplifies to be 4I root 6. And again, the order in which you write those doesn't matter. If you say I 4 root 6, exact same thing. Root 6 4I, exact same thing. All right, and then just real quick, why don't we do 2 minutes to simplify the square root of -25 and also to simplify -8, square root of -252. Let's check these last two. And root -25, well, after taking out the negative and calling it imaginary, I immediately recognize that square root of 25 is a perfect square. And so I take square root of 25 as just 5. Those get sneaky when we start mixing in like perfect squares, especially ones that we don't recognize. Like I know on one of your homework problems for the quadratic formula tomorrow, there's like a really big square root. Like I think it's, I shouldn't say really big, but it's like 21 squared or something. So a lot of times if you, like 441, if you're working with a big number, a good place to start might just be making sure that that's not a perfect square, right? Because even me, like I could list off up to 13 squared. Okay, but after that, I'm not going to recognize the perfect squares. And for you all, it might only be up to like 100, right? You may only say, yeah, I know hundreds of perfect square, but after that, we don't recognize them. Okay, so for a lot of you, when you see a square root, first just make sure that it's not a perfect square on its own. Okay, but it is here. Right, then the last one, that -8. Remember that negative, it doesn't make this imaginary. Not the negative in front of the 8, it's a negative underneath the square root. So taking out that negative, that makes this imaginary. And the largest perfect square that divides 252 is 36. Really easy to divide out 16 there, or even 4, which is fine. Just know that you have a little bit more work to do if you aren't taking out the largest perfect square. Okay,